Okay, so let's get these discussions underway. The first problem is chapter 15, problem 5, point A. We're asked to find the force between two alpha particles when they are 5 times 10 to the negative 15 meters apart. So we have, let's draw this like so. These are two alpha particles. They have 2 protons each, right? Okay, that's easy enough. So we want to find the electric force between them, and that's going to be just like an electric field, K over R squared, but it's the force between the two charges. Right, so we have Q1 and Q2. Okay, so that gives us, so K here in this case is 8.9 times 10 to the 9 newtons meter squared per coulomb squared. And then we multiply. So we have, our charge is two protons each, and we square that, right? Because we have one charge that's 2 protons and another charge that's 2 protons. Okay, and the distance then is 5 times 10 to the negative 15 meters, and that's also squared. So we plug this in. Let's just copy this real quick because I didn't actually, let's do this. How about, let's write down the actual value of the charge so that we can see what we are working with here. There we go. Okay, so we plug all this in, we end up getting 36.8 newtons. Fairly straightforward. So remember, the main thing to remember here is just we have an electric field, but we want to know the force between the two charges, so we multiply by the other charge over the distance between them, right? Next problem. 5.6. Okay, we're told a molecule is 2.7 micrometers long, and the ends of the molecule become singly ionized, negative on one end, positive on the other. The helical molecule acts like a spring and compresses 1% upon being charged. Determine the spring constant. Okay, so we have singly ionized, so here's a positive charge, here's a negative charge. And then when that happens, the distance is compressed by 1%, so that gives us left over 99% of the total length. Okay, so since we're modeling this as a spring and we have an electric force, we can equate the two forces. Right, we have Hooke's law and we have our electric force. So in this case, for the electric force, we have K times our positive charge and times our negative charge, the two charges, right, over d squared, which would be the total distance here. This is where our electric force comes in. And then we have our spring Hooke's law force, which is also kx, which will be the distance that it actually is compressed. So this is 1% of the distance compressed. Okay, so the total overall electric force, let's calculate that. So here's the distance, e to the negative 6. This is the same way. I write this convention a lot. This is the same as writing 2.17 times 10 to the negative 6 meters. Because that's how you have to enter it into a calculator, so I just got used to writing it that way. And then we have this. Positive and negative charge. This is going to give us, by the way, this is our electric force, like I said. This is going to give us let me just make sure I wrote everything down correctly. Yeah, this is going to give us about 4.9 times 10 to the negative 17 newtons. This is also squared, so that's what I did. So I did miss the square, so make sure that you square the distance in your force. Okay, so that's the electric force. Now let's calculate the Hooke's law force. So what do we have? We know what the force is, so let's do this. So we know what our total force is. It's this value here. We just calculated it. So let's enter that. 4.9 times 10 to the negative 17 newtons is equal to kx, which is x is the distance that I mentioned earlier. So that's going to be 2.17 e to the times 10 to the negative 6 meters times 0.01. That's 1% of the distance, because that's what is compressed, right? So now we want to find the spring constant. So then we take 4.9, 10 to the 17 over 2.17, 10 to the negative 6, 0.01. Make sure we have our units. And this gives us 2.25 e to the negative, let me just double check, 9 newtons per meter. So we were able to do that by equating the two forces, Hooke's law for the spring and the electric force. Okay, I'm going to post the next two problems on another video.